Okay, today I want to talk about a universal terminal for mobile edge quantum computation. To bring the quantum capacity to the society, one approach is to use the um, cloud computation. The optimum approach here is to have simple, non-error corrected personal devices that offload the computational tasks to the quantum computers via edge servers that features cryogenic components and fault-tolerant schemes. So here we have a network of elements that deploys different encoding approaches. Um, and this presentation proposed a quantum terminal that is compatible with different encoding protocols, paving the way for mobile edge quantum computation. So the scheme is shown in figure 1A. Here we have two processors that are using different encoding protocols. The left one uses 4-qubit encoding and the right 6-qubit encoding. And I have a central atom that is responsible for photon emission at an early or late time, depending on the state of the logical qubit encoded on the placket atoms. The emitted photonic qubits would then go to the entanglement swapping station, where a projective Bell state measurement would entangle the far separated logical qubits in their own logical basis. So the level scheme of the central atom is presented in figure B. I have a lambda configuration that is responsible for photon emission, and the omega S laser is the atom light coupling, atom laser coupling. G is the atom cavity coupling. And over this process, I go to the E electronic state and emit one and excite one cavity mode, which would then leak out of the cavity and emit a single photon with the gamma C rate. And this lambda transition is controlled by a Rydberg laser. And this Rydberg state would have different energy levels depending on the state of the logical qubit, as I will discuss later. If the laser would be in resonance, it would block the transition by quantum interference effect. The laser would only be in resonance if we have one logical state, and if we have zero logical state, it would not be in resonance, and then allows early photon emission. So the pulse sequences are shown in figure C. You can see that we have an early set of pulses that contains omega S and omega R, and we have a late pulse that is only omega S and no omega R is accompanied. So in the early setup, if we have zero logical qubit, we emit a photon. If we have one logical qubit, we don't emit an early photon. And then if in case of one logical qubit, we then emit a photon at a late time where we don't have the blocking omega R laser anymore. So with this mechanism, we entangle the logical qubit and the time-being photonic qubit with an example that is shown, for example, in equation 2. So how does a central atom sense the logical qubit that is encoded on the placket? It is based on Rydberg Fermi sensing. And this approach, I suggest to encode the information in dual space. It's both space and electronic basis. So I use a spin-dependent lattice, and in this configuration, the placket atoms would, with different qubit states, would be stored in different places in a space. If you see figure E, I show the central atom and two of the placket atoms, and you can see the wave function of the central Rydberg electron. And the placket atoms would only be inside this wave function if they are in zero qubit state. Otherwise, they would not feel the electron scattering. And the qubit-dependent level shift of the central atom is occurred by the Fermi scattering of the electron from these 3D geometry. In the paper, I also discussed the dynamics and the analytics behind this entangling mechanism. And I discussed that when we have one logical state, the laser would be in resonance, and we have a dark and bright state, which would be degenerate. And then there would be a quantum interference that blocks the E emitting state totally. But when we have zero logical state, there is no Rydberg laser resonance, and then the degeneracy would be lifted, and the system would follow the darker state and of the lambda configuration and emit a photon. I also discussed the rate of photon emission out of the cavity, and some of the bold results that I share here are shown in these three figures. In figure A, I discussed that there is a minimum detuning above which we can lift the interference of dark and bright state in case of zero logical state, allowing early photon emission. In figure B, I discussed that there is a maximum limit for the emission of the cavity. Large cavity leakage would reduce the coherence, scatter the population out of the dark state, and reduce the emission probability. And in figure C, I discussed that in case of one logical qubit, if we want to have perfect fidelity above 99% fidelity, omega r must be larger than 3 times omega s. And at the end, I discussed the logical operation with 6 qubit encoding. I designed a Rydberg cloud that could operate in the logical qubit of 6 on a hexagonal structure. And thanks for your attention.